So for this session, we'll be having lecture number 3. So this is antiderivatives. So what is this antiderivatives? A function, capital F, is called an antiderivative of a function small f on an interval I if the derivative of capital F is equal to small f for all x in the interval I. Okay? So take note, here you have capital F of x and then you have small f of x. Okay? So from small f of x, we can get f prime of x. So we say that this guy here, this is the derivative, okay? Derivative of small f. Okay? Now, if this f of x is equal to this capital F of x, okay, then, if this small f of x is equal to capital F prime of x, then we say that function f, okay, the one that we take the derivative, okay, that is called the antiderivative. Okay, is that clear? So again, you have a small function f. If you get the derivative of that, you will have small f prime of x. This is derivative of f. However, if you go up, okay, you found this capital F such that the derivative of capital F, it's small f. Then capital F is antiderivative of small f. Okay? So for example, if we look at this capital F of x to be x squared, okay, take note that capital F of F prime of x, this is equal to 2x, okay? So, if your F of x is equal to 2x, then capital F of x is an antiderivative of small f of x, okay? So you have capital F of x, you get the derivative of capital F of x, that will become your small f of x. Okay? Also, if we have this, the function capital G of x, which is equal to 2 cosine 3x minus x plus 1, this is an antiderivative of this small g of x. This is equal to negative 6 sine 3x minus 1. Okay? And again, that's because if you get the derivative of capital G, you will get what? 2 times the derivative of cosine 3x, that's negative sine 3x. Then by chain rule, you have to multiply by the derivative of 3x. And then minus the derivative of x, it's just 1. And then here, derivative of constant, that's just 0. So if we simplify this is equal to, you have 2 times negative sine 3x times 3. So you will get negative 6 sine 3x. And then you have minus 1. And this is precisely your small g of x. Okay? So derivative of the capital letter equals the small letter. And therefore, the capital letter is antiderivative of the small letter. And if you have noticed, I use capital and small letter correspondingly, in a sense that if I used capital letter F for an antiderivative of some function, then that some function is the small f. If I have capital, say, H, okay, If I have some capital H here, then correspondingly, I will use small h. Okay? So this is small h such that capital H prime equals small h. Okay? Questions? So it's plain definition. Now, an antiderivative of a function, small f, this is not unique. As you can see here, I use the word "an" here. Okay, this guy here or this guy here to mean that there are other possible antiderivatives. In fact, there will be infinitely many of them. Okay, so an antiderivative of a function, small f, it is not unique. Okay, if capital F is an antiderivative of small f on an interval I, and c sub 0 is a fixed constant, then this another function here, capital F of x plus c sub 0, this will also be an antiderivative of small f. Okay? Why? Because you have this function, capital F of x plus c sub 0. You get the derivative of this. If you get the derivative of this, of course, you just have to get the derivative of capital F, that's your f prime of x. And then this is a constant, the derivative of constant, it's equal to 0. Okay? But capital F of x, okay, capital F here is an antiderivative of small f. Therefore, the derivative of capital F must be small f, which means this guy here, this new function here, okay, has derivative small f. Therefore, this function here is also an antiderivative of small f. Okay? So meaning, if you got an antiderivative, just add maybe 1, you have another antiderivative. Or add negative 5, you have another antiderivative. So you will have infinitely many antiderivatives. Okay? Now, if capital F is an antiderivative of small f on an interval I, then the most general antiderivative, take note of this, then the most general antiderivative of small f on I is capital F of x plus constant, where this constant is arbitrary. Okay? Meaning you don't have to replace this with specific number. Okay? And again, the proof, it's just like this. Since c is a constant, although you don't know what constant you want to use, the derivative of that constant will always be 0. So this function here is still an antiderivative of f. And we call this the general antiderivative. Okay? For example, f of x equals cosine of x, okay, where x is any real number. Then this capital F of x, which is equal to sine x plus c, this is the general antiderivative of small f. And again, the proof is simply you get the derivative of capital F of x. So you're just getting the derivative of sine x plus c. Okay? But you have the derivative of sine x, that's cosine x, and the derivative of constant, it's just 0. And this is your small f of x. So this is the general antiderivative of cosine x. Okay? Next example, suppose your g of x equals 1 over x, where x is from 0 to plus infinity. Then this function here, capital G of x equals ln of x plus any constant c. Okay? So this is the general antiderivative of this small g. Again, just get the derivative of your capital G. I hope you still remember the derivative of ln of x. Well, that's just 1 over x. Okay? And this is precisely your small g of x. Okay? Another function here, h of x equals x raised to n, where x is from 0 to plus infinity. And your n here, it's not equal to negative 1. Okay? The case n equals negative 1, it's this guy here. Okay? Because x raised to negative 1, that's just 1 over x. So we remove the case n equals negative 1. Okay? So small h of x equals x to the n, where x is from 0 to plus infinity, and n not equal to negative 1. This function here, h of x, capital H of x, which is x raised to n plus 1 over n plus 1 plus the arbitrary constant c. This is an antiderivative of small h of x. And again, to see that, all you need to do is to get the derivative of capital H. So you have x raised to n plus 1 divided by n plus 1 plus the constant c prime. And you remember your power rule. So n plus 1, it's just a constant. So x raised to n plus 1, you get the derivative. You just use power rule. N plus 1, x raised to n plus 1 minus 1 divided by n plus 1. And derivative of c, it's again 0. But now you can cancel n plus 1 here and n plus 1 here. So this guy here will cancel this. While the exponent, you have n plus 1 minus 1. And so you will just get n as the exponent. And therefore, since this is your small h of x, capital H here is an antiderivative of, or it's actually the general antiderivative of small h. Okay? Questions so far? Now this guy here, small f of x equals 1 over 1 plus x squared, where x is any real number. We take capital F of x to be the tangent inverse of x. Remember your tangent inverse or your arctan? Okay? So tangent inverse of x, this is your arctan of x. And let me recall the other inverse trigonometric function, sine inverse of x, or this is arc sine of x. And maybe let us also recall cosine inverse of x. This is your arc cosine of x. Of course, you have your arc cotangent, arc cosecant, and arc secant. Okay? Similar way of writing. And recall, you have to remember the derivative of your arctangent. Okay? This is equal to your 1 over 1 plus x squared. You have to recall that one. So we have here f prime of x equals, you have the tangent inverse of x plus the constant c You get the derivative of this. This is 1 over 1 plus x squared. And this is your small f of x. So this function here, okay, which is tangent inverse x plus c, that is the general antiderivative of the function f of x equals 1 over 1 plus x squared. Okay? Questions so far? Now, one application of these antiderivatives is solving what we call initial value problems. Okay? So what are these initial value problems? These are problems where our goal is to find particular antiderivatives. Okay? That is, we want to find a particular value for C satisfying the conditions of the problem. Okay? So this one, initial value problems in relation to antiderivatives. Okay? In general, if you have an initial value problem, the problem could have a general solution. Okay? But the goal there is to find a particular solution. Okay? So in our case, as an application of antiderivatives, the solutions to our initial value problems will be something like an antiderivative of some functions. Okay? But we will start with the general antiderivative that will become the general solution of the problem. There will be initial values or initial data in the problem. And using that initial data, we will then try to get the particular solution. So from the general solution, we use the data that is given to us, and then we find the particular solution. In our case, since our general antiderivative, you have plus c there, our goal is to find a specific value for the plus c there, or the c there, such that that value of c plus the function or plus the antiderivative will satisfy the condition of the problem. For example, you have, so we want to find f of x, okay? We have to find this function f of x if f prime of x, this is equal to cosine of x plus 25 times 1 plus x squared raised to negative 1, and such that your f of 0 equals negative 1. Okay? So we want to find f of x if f prime of x equals cosine x plus 25 times 1 plus x squared raised to negative 1, and that f of 0 equals negative 1. Okay? Now, how does this one relate to our to antiderivatives? Notice you have here small f of x, and then you have here f prime of x, small f prime of x. So, in order to relate this to the antiderivative problem or antiderivatives concept that we just discussed, okay, what we can do is to let, okay, let g of x, okay, let g of x, this is equal, this is equal to your f prime of x, okay? And then your capital G of x here is is such that G prime of x, this is equal to small g of x. Okay? Actually, not that one. My g of x, this is your small f of x. Okay? So that if I get the derivative of this guy here, okay? If I get the derivative of your capital G here, this will become small g, correct? Indeed, capital G, it's your small f of x. If I get the derivative of capital G, I'll also get the derivative of small f. But the derivative of small f, that is your small g of x. So what does this mean? We want to find small f of x. But small f of x equals capital G. Such that if we get the derivative of that small f of x, we will get small g of x. In this relation here, this means, okay, this means that we want an antiderivative, an antiderivative of g of x. The antiderivative of small g of x, that will be your capital G. Correct? And therefore, that capital G is the one that you are looking for. That is your small f of x. Now, now, you are given g of x equals, according to this is your f prime of x. But your f prime of x, it's this guy. Cosine x plus 25 over 1 plus x squared. And we now know that the function capital G of x, you get some function whose derivative is cosine x, that will become sine x. And you need a function whose derivative is 25 over 1 plus x squared. So that's 25 tangent inverse of x plus c, where c is arbitrary. This function here is the general antiderivative of small g of x. Well, because if you get the derivative of this, you will get this cosine x plus 25 over 1 plus x squared. Following? Okay? Okay. So, we now know our desired function. We now know our desired function here. That's sine x plus 25 arctan of x plus plus arbitrary constant c. Okay? So from here, we take f of x to be sine x plus 25 arctan of x plus arbitrary constant c, where c is arbitrary. Then we get the derivative of f of x. So this is just derivative of sine x plus 25 tangent inverse of x plus c. And this is exactly cosine x plus 25 over 1 plus x squared. So at least this part here is satisfied. So the first condition here, it's satisfied. Meaning, we are in the right track of finding the small f of x. Now, according to the condition, additional constraint here, or additional condition here, your f of x, or your f of 0 equals -1. But this is our function. Okay, this is our function. But f of 0, this is equal to sine 0 plus 25 arctan of 0 plus a constant c. But sine 0, that's just 0. Arctan of 0, that's also 0. So this is just c. Meaning, this c here, it's equal to -1. Okay? Therefore, the desired function, is, so the desired function is, you now have f of x equals sine x plus 25 arctan of x minus 1. Okay? Questions? Let's have this. Find f of x if f double prime of x equals 12x cubed plus 6x squared minus 5 if f of 0 equals -2, equals +2, and f prime of 1 equals negative 1. Okay? So, just like before, this is an antiderivative problem. So, we have function f. We go down to your f prime, and then we can still go down to f double prime. So this is our function, or this is the function given to us, f double prime of x. That's your 12x squared, x cubed plus 6x squared minus 5. So we need to go up. We need to find that f prime of x. And once we know the f prime of x, we can use it to find our f of x. Okay? So basically, it's like this is your um, small g of x, and then this becomes your capital G of x, because if you get the derivative of capital G, you are getting the derivative of f prime. And the derivative of f prime, it's f double prime. So the derivative of capital G equals small g. So it's an antiderivative problem. And then maybe you can think of capital G as small h of x. And then this f of x, h of x, small h of x, that's your capital G. And then this function, small f, this is your capital H of x. And again, if you get the derivative of capital H of x, that means you are also getting the derivative of small f. And that's f prime. But f prime, that's your small h. So again, antiderivative problem. Okay? So let's start with getting these antiderivatives. Let's start from second derivative here to first derivative. Okay? So let me erase these letters here. So what? According to this guy, this here, we can use this. H of x equals x to the n. Then capital H of x, it's x to the n plus 1 over n plus 1. Okay? So we will use that. So in here, it seems that we can take our f prime of x. Okay? We can take f prime of x to be 12 x raised to 4 divided by 4. So we use this x cube. We add 1 to the exponent, and then we divide by the new exponent. That's why we have here x to the 4 over 4. And then plus, we have 6. This time you have x squared. So you add 1 exponent or 1 power. And then you divide by that new power. And then minus 5x. So how is that? Take note, 5 here, it's just 5x raised to 0. And by definition or by convention, x to the 0 is just 1. Okay? If x is treated as a variable. So x to the 0, it becomes x to the 1, then over 1. So you just have the over 1 there, but again, it's just the same. Okay? And then, of course, we have the arbitrary constant. Okay? We have this c here. Let me label this as C sub 1. So this is our f prime of x. And then we simplify. Let's just simplify this. You have 12 over 4, that's 3. So you have 3x to the 4 plus 6 divided by 3, that's 2. So 2x cubed. Then here we just have 5x plus the arbitrary constant c sub 1. This is your f prime of x. And according to this, f prime of 1 must be equal to negative 1. F prime of 1, this must be equal to negative 1, which means that your negative 1, which is f prime of 1, this is equal to 3 times 1 raised to 4 plus 2 times 1 cubed minus 5 times 1 plus c sub 1. So if we calculate this, we have 3 plus 2, that's 5, minus 5. So c sub 1. C sub 1 equals negative 1, which means that f prime of x, this is 3x to the 4 plus 2x cubed minus 5x minus 1. Okay? This is just your f prime of x. We want f of x. Okay? So let us continue. What we had was f prime of x equals 3x to the 4 plus 2x cubed minus 5x minus 1. Let us check. So 3x to the 4 plus 2x cubed minus 5x minus 1. Okay? To get f of x, again, we use the same formula that we have previously. We will now get f of x. This is 3x raised to 5. So you have 4 plus 1. That's 5. So we divide this by 5 plus 2x to 4 over 4. Again, that's 3 plus 1. Okay? Then minus 5x squared over 2. The power of x here, it's 1. So we have 1 plus 1. And then we have minus 1 times x. So we just have x. Again, x to the 0. So power is 0. We add 1 to the exponent. So we will get x to the 1. And then plus the arbitrary constant c sub 2. Okay? And then, according to this, now we have f of 0. This is equal to this is equal to positive 2, according to this guy here. So, 2, this is f of 0. All these guys here, this guy here will be 0, this guy here will be 0, this and this, they will be 0. You'll be left with c sub 2. And therefore, the desired function is f of x equals 3x to the 5 over 5. And then here I'll just simplify. So plus x to the 4 over 2 minus 5x squared over 2 minus x plus c sub 2, but c sub 2 it's equal to 2. So plus 2. So this is the desired function. Okay? Questions? Now, other applications of these antiderivatives and derivatives and initial value problems. We have the following: rectilinear motion, motion along a straight line. So in here, suppose we have s of t. This is the position function. If we get the derivative of s of t, what we will get is a velocity function. If we get the derivative of the velocity function, we will get the acceleration function. Okay? Take note, position function, derivative of that is velocity function. And then derivative of the velocity function, acceleration function. And you might be thinking, sir, what about speed? The speed function. The speed function is different from the velocity function. Okay? Take note. Velocity, it has magnitude and direction. While speed, you just have magnitude. Okay? So from here, suppose a particle moves in a straight line and has acceleration given by a of t, centimeters per second squared. Its initial velocity is negative 6 centimeter per second, and its initial position is 9 centimeters. Find its position at any time t. So take note, a of t, this is the derivative of v, okay? And it's the second derivative of your s. So if you look at this, you have s double prime of t, you go up to s prime of t, you go up to s of t. But again, this guy here, it's your b of t. Okay? Here, you have your b prime of t. So from b prime of t, you go up to find v of t. And v prime of t, this is your a of t. So basically, you have to go up twice from a of t to find s of t, to find the position of the particle at any time t. So let's work on this. A of t, it's 6t plus 4. Okay? Then this is your b prime of t. So maybe we can take b of t equals 6 t squared over 2 plus 4t plus c sub 1. It's because if you get the derivative of this, you will get a of t. Okay? So this is simplified into 3t squared plus 4t plus c sub 1. It is said that the initial velocity is negative 6 centimeters per second. By initial, it means t is equal to 0. Okay? So initial velocity, this is the velocity at t equals 0. and it's said it's -6. And therefore, if it is -6, you look at this. So -6 equals v of 0, but this is your function. So you'll just have 3 times 0 squared plus 4 times 0 plus c sub 1. And this is just your c sub 1. Therefore, b of t, this is 3t squared plus 4t minus 6. Okay? What about s of t? v of t, this is s prime of t. Okay? So v of t is an antiderivative of s. Or no. V of t is the derivative of s. So s of t, it's the antiderivative of v. Okay? So v is the derivative of s. Therefore, s is an antiderivative of v. So to get s, we have 3 t cubed over 3. And again, we just add 1 to the exponent 2 here. That's why it becomes 3. And divide it by 3. Plus, here, power is 1. So we will have 4t squared over 2. Then here you have 6t, because again, you have t to the 0 here. And then plus c sub 2. And if we simplify this, we will have t cubed plus 2t squared minus 6t plus c sub 2. According to this, the initial position is 9 centimeters. Okay? So initial position, so it means it's the position at t equals 0. So s of 0 equals 9. And we shall see, we have 9 equals s of 0. This is equal to 0 cubed plus 2 0 squared. 2 0 squared minus 6 times 0 plus c sub 2. And this is just your c sub 2. Which means the position function at any t, this is the position function now. We have t cubed plus 2t squared minus 6t plus 9. So quantity, this is centimeters. So this is the desired function. Okay? Questions? One more problem here. A ball is thrown upward with a speed of 48 feet per second. Take note, speed. From the edge of a cliff 432 feet above the ground. Find its height above the ground t seconds later. When does it reach its maximum height? When does it hit the ground? So let us try to visualize this. So suppose this is the cliff. Okay? Ball is thrown upward. So you have the ball here, and then it was thrown upward. And of course, it should go down eventually. Okay? The height is what? The height of the cliff is 432 feet. So this guy here, this is 432 feet. Okay? So the problem is find its height above the ground t seconds later. When does it reach its maximum height? So we will also find the maximum height here and the time, okay? And the time it reached that height. And then we will also find the time the ball reached the ground. There is no function here, at least based on this problem up to this part. But according to this hint, we use acceleration due to gravity. It's 32 feet per second squared. So we have here actually the acceleration function, a of t. Okay? And a of t here, this is equal to negative 32 feet per second squared. Due to gravity, because the positive side, it's going downwards. Take note of that. So we have here negative. Okay? We have here negative 32 feet per second squared for the acceleration function. The gravity, it's always going downwards. Okay? That's why we use negative. Okay? So let me remove first this unit here. This is our a of t. This means that our v of t, this is equal to negative 32t plus constant. But it is said the speed is 48 feet per second. The speed, it's just the magnitude. In fact, it's the absolute value of the magnitude of this v of t. Which means that v of 0, this is given to be 48. So when this ball was thrown up, it has the speed 48 feet per second. Okay? So if v of 0 equals 48, this means that we have 48. This is equal to v of 0, but this is equal to negative 32 times 0 plus c sub 1. And therefore, the velocity function, this is equal to negative 32t plus 48. Okay? And then we need the height function or the position function. So from v of t, we'll compute for s of t. So we had obtained v of t equals negative 32t plus 48. So s of t, this is equal to negative 32 t squared over 2 plus 48t plus c sub 2. Okay? But now, we have here initial position is at 432 feet above the ground. So S of 0, so this is not implication. Now, S of 0, it's equal to 432 feet, which means that, okay, which means that 432, this is equal to S of 0. And if we simplify this, negative 32 over 2, that's just negative 16. 0 squared plus 48 times 0 plus c sub 2, and this is just c sub 2. Which means that the position function, okay, S of t, this is equal to negative 16t squared plus 48t plus 432. Okay? So this is the height function. The next problem here, when does it reach its maximum height? Let us go back to this. It will reach the maximum height at this particular point. But how do we calculate that? Remember, you have a velocity. It has magnitude and direction. Okay? So your function, your position function, it will go up here and then it will go down. It will change direction at this particular point. But what does this mean? At this particular point, at that particular instant, the ball is not moving. Correct? At that particular instant, the ball is not moving. Of course, your ball, it will go up, go up, go up, and then at this particular instant, it should stop and then starts to go down. But if it stopped, what does it mean in its velocity? The velocity is equal to 0 at that particular moment. So to answer this second question here, we need to find the value of t for which the velocity is equal to 0. Okay? We need to find the value of t such that the velocity is 0. So for the next goal, find t such that v of t equals 0. And our v of t, this is negative 32t plus 48, and we want this to be 0. What does this mean? You have 32t equals 48, or t equals 48 over 32. But 48 over 32, this is just 3 over 2. Okay? So after, at the point 1.5 seconds, that's when the ball reached its maximum height. So the ball reached its maximum height 1.5 seconds after release. Okay? Questions? For the last problem here, when does it hit the ground? If you look at this is the ground. And our initial position is 432 feet. Meaning, this position, we assume it the zero position. Correct? The ground, we assume that as our zero position. So to find that, okay, to find the time, what we need is to solve for t such that s of t is equal to 0. Okay? So for the last problem here, find t such that s of t, this is equal to 0. But what is s of t again? It was negative 16 t squared plus 48t plus 432. So we want this to be 0. Okay? And then maybe we can factor this. You can solve using quadratic formula if you want. You can also do factoring. Okay? You can factor this. Okay? So this means you have negative 16 times t squared minus 3t plus 27. Sorry, minus 27. 432 divided by 16. Is that correct? 432 divided by 16. Yeah, that's 27. Okay? So you have this, and you want this to be 0. So you can solve this using quadratic formula. Okay? 27, that's 3 times 3 times 3. So we can only use 3 and 9. But that will not give me the middle value 3. So let's just use quadratic formula. So t equals negative b. Okay? That's 3 plus minus square root of b squared. So negative 3 squared minus 4 times 1 times negative 27 all over 2a. So this is equal to 3 plus and minus square root of 9 plus 4 times 27, 108 all over 2. So 108 plus 9, that's 117. Okay, so this is equal to 3 plus and minus square root of 117 over 2. And then let us estimate this. 117, if we get the square root of that, we will get what? 10.81 approximately. Okay? So approximately 3 plus and minus 10.81 or 10.82. 10.82 over 2. Okay? But take note, 3 minus 10, that will be negative. Okay? That will be a negative number. And we are talking about time. We don't have negative time. Okay? So, our conclusion, the ball will hit the ground, will hit the ground after we take the addition. After, so 3 plus 10.82, after around 13.82 divided by 2 seconds after release. Okay, so I'll remove this party. Okay, so the ball will hit the ground after around 13.82 divided by 2 seconds. Okay, questions? Any questions so far? So this will be the last problem for this part. Okay.